So we were talking about bathtubs earlier in the stream. So let's clear this. Okay. So basically a drawing of what's happening here. You have like this. Oh, whoops. Good thing we can erase. Okay. This is really poorly drawn thing of what's going on. Okay, and then we have the ball that's actually a circle, and we have fluid flowing. So the reason is actually lubrication. Okay. So there's a very thin layer right here that makes this very smooth, and the ball, when you expand it out, so if we expand out this bit, we get something that can be estimated as a parallel plate liquid flow. So this is like the sphere, and this is the edge. So it's approximately linear because this scale is so much smaller than the diameter. So when you expand it out to look at just this area, it's such a small part of the sphere that it's about linear. And so when we have fluid flow like this, ignoring like the fluid falling, we get what's called a parallel plate fluid flow. So if we assume that it's not turbulent, because that complicates a lot of things, and I don't know how to do that yet, and then we take a line of fluid, what happens is we get something like parabolic, and it has 0 here and here. So it turns out that because of the lubrication and the force that this fluid can exert on this ball is actually extremely like efficient and high enough that you only need about 8 psi gauge. So the pump needs to be 8 psi. So you only needed 8 psi to support 29 tons, which is crazy. For reference, atmospheric pressure is 14.7 psi. That's your interesting chemical fact. So there are molecules that are called stereoisomer. So they have the same atom connectivity, the same bonds, and all of that stuff. But the only thing that's different about them is some sort of geometrical orientation. So one class of these isomers make up a lot of different DNA things. So a lot of the molecules that make up DNA, they're what's called chiral molecules, the amino acids. And so what a chiral molecule is basically if you take the molecule and you flip it over like a pancake, or mirror it, not just flip it over, but you mirror it, then it's different than its other mirrored form. So you can think about a chiral molecule like with your hand. Your hands are actually chiral. They're mirror images, but then if you try and superimpose them, you can't do it. Your thumbs don't line up. And it's palm to the back of the hand, so they don't superimpose. And no matter how you do it, you can never get your thumbs to line up unless they're mirrored. So those are what's called a chiral molecule. And chirality can actually have some interesting properties because uh, there are certain, especially in medicine, there was I'm blanking on the name, but there was a drug that's used to treat morning sickness, and if you have one form, then it's or wait, are these for an enantiomer? I'm pretty sure it's by chirality. It might be the other isomer thing. The other stereoisomeric property. I'm pretty sure it's chirality. One form of the molecule actually treats morning sickness. The other form of the molecule is toxic to babies. So toxic to unborn. So this stuff is really important when you're medicine. You have to like know what molecules you're using. Okay, so we're gonna talk interesting chemical fact in the sense of, I guess we'll talk about like some quantum mechanics stuff, which is really exciting. So, ooh, some Boltzmann stuff. I'd like to know about the Stefan Boltzmann. That's a Boltzmann. Actually, I might know this, but I don't. Let's see. Describes the power radiated from a black body in terms of its temperature. Specifically, the Stefan Boltzmann law states that the total energy radiated per unit surface area of a black body across all wavelengths per unit time star, known as the black body radiant admittance, is directly proportional to the fourth power of. Oh yeah, so I actually know how to do this. We learn about this in heat transfer. So I guess it's called the Stefan Boltzmann law. So we learn about radiation in terms of anything, not just black bodies. It looks like black bodies is a little bit more complex, but there's this thing called Newton's law of cooling. And so Newton's law of cooling basically states that if you have a interface with a fluid where there's a temperature gradient between the interface, the surface temperature on the interface, and the atmosphere or the surrounding temperature, you'll get a called convection. So convection is a boundary condition, and it happens when your surface is a different temperature than your. So in Newton's law of cooling, the convection term or the radiation term is very similar to Newton's law of cooling. It's not the same thing, but the actual, where are we at? Monitor. Okay, so Newton's law of cooling says the heat transfer coefficient, and then so heat flow is equal to the heat transfer coefficient times area times delta T, the negative equals heat flow. So the term for that's similar to this. Oh gosh, make sure that I'm not throwing the game while the similar term. Did we let? Oh, we lost. Okay. The similar term for radiation is here, and so it says that the radiation heat flow is equal to this times negative, is it? Delta T the fourth. So this means you fourth power your T's. So instead of like T atmosphere minus T surface, it would be like T atmosphere to the fourth minus T surface to the fourth times area. So that's the radiation term. So it's not surprising that in this law that I just looked up, the dependence, the proportionality of radiation of a black body to temperature, not surprising that the fourth power, because that's just like what radiation is. So there you go, buddy. There's your interesting chemical fact about radiation. So radiation, well, actually, hold on, it's not over yet. Radiation is actually there because it helps. It makes it so that things can't blow up in temperature. So there's a limit of how hot things can get, and if you didn't have radiation, you'd have like runaway. Pretty cool. That's not why it's there, but that's what it does. Alright, there it is. Alright, interesting chemical fact. So, There's a so chemical engineering. This is more of a chemical engineering fact. So house operated. Um, so basically, with chemical engineering, it's really complex, right? So we're trying to model complex situations using as much knowledge as we can of the system, but if you try and exactly model some things, it gets really messy really quickly. So like my heat transfer equations can get like two two lines of a page long, and I write small. So you can get really large equations. So in chemical engineering, it's kind of interesting. I used to have this idea that we would just use those equations or whatever, but in fact, what we do is we use these things called dimensionless parameters, and these dimensionless parameters just kind of give you like an intuition of what is going on in the system. So one such parameter is called the BO number, and the BO number is basically a number that explains or gives you a ratio of the convection effects compared to conduction effects in a material. And so if you have a high BO number, that means that your convection is much, much larger than your conduction, which means that you're limited by conduction and it's what's called good convection. And so this means that the material is basically the temperature of the surrounding atmosphere. If you have a low BO number, it's the opposite. The material is basically one temperature um, throughout, and it's not the. So that's your interesting chemical fact. We use all these numbers. We have a thing called a Reynolds number. Well, but we'll save the explanation of the Reynolds number later. Okay, that's interesting. All right, interesting chemical fact. So we're doing a chemical engineering fact today. Did you know that if you have fully developed flow in a pipe that is laminar, then the way that the flow happens, the velocity profile is actually like a little bow and arrow. Like if you take a line of particles straight down and you measure their velocity, then their velocities will form a kind of like normal distribution looking. It has nothing to do with normal distributions, but it looks like a normal. So like, I can even show you guys with zones. Alright, so if this is your velocity profile, then your velocity, let's say this is a pipe wall right here. Then the velocity right here is 0. And then the velocities grow up like this. I don't actually want to do this whole so. So then your velocities look like that if this is the other pipe wall. So that is what a velocity profile. What is going on? Okay, this is what a velocity profile would look like in a pipe. Okay, this should be. So there's this thing called a no-slip condition. And basically, if you have a particle that's on the wall, it has to have the same velocity as the wall. That's how it works. So because of the no-slip condition, if this isn't moving, then this isn't moving. Right? But that's only on a solid, liquid, or fluid, solid fluid interface. There you go. Now you guys know how to draw the velocity profile in a fully developed steady state laminar flow cylindrical pipe. And so that velocity profile, that's only in one cross section, but it rotates around. So it's like the velocity in the middle is the maximum velocity that you get. And if you have a steady state incompressible fluid, which means the density can't change, then your velocity will be constant in the z, in the direction of the flow, I guess. Look at that, you guys are helping me study for my quiz on Monday.